everybody, and welcome to our first lecture for number theory with me. We're going to be talking about modular arithmetic. What we're going to be building up to is sets and set operations where you end up with non-zero elements that multiply to zero, which I first saw that and my mind was blown. So first thing I'm going to do is ask you to recall a couple of things for me, which is x is equal to y mod m when m divides x minus y, and then this might be a little bit more of a reach, the equivalence relation where we use a is related to r if we're using the modulus. I know that we did this specifically for, I think it was 3 on a worksheet. You proved it was an equivalence relation, but just to make sure that you guys feel comfortable with that, you guys will be proving that's an equivalence relation on the worksheet today. And so I would actually suggest pause the video right now, go prove it. That way when I use facts about this being an equivalence relation, you're not like, how does that work? Okay. But nice warm up for right now. We're going to prove this theorem. The theorem says that if A and B are congruent modulo m, then we can have a k that multiplies by m, and we'll get A equals B plus some number of m's. So basically you take B and you keep adding or subtracting m until you eventually get to A. So let's check out why this works. Falls out pretty quickly from the definition. So we assume that A and B are congruent modulo m, which is the same thing as A is congruent to B mod m. And then what that means via the definition is we have m divides A minus B. That's definition of mod. And then where are we trying to get to? We're trying to get to an equation that looks like so. A equals B plus Km. So let's try and interpret this. We have the definition of divides, so we can apply that now. We can say A minus B equals M times K. This is definition of divides. And then if you just add B to both sides, we're done. We've gotten there. Then that was the forward direction. So the question is, what about the backwards direction? So first thing we do is we ask, can we be lazy? Does this stuff reverse? Yes, it does. Does this stuff reverse? Yes, it does. That is just the definition of divides. And that step also reverses. That is definition of modulus. So we're all good. All those flipped around real nice. So we get rid of all of our extra things that we don't know or don't need. We still know them. There we go. And we're done. We're going to use this to define something called a congruence class. So if you've got a number A and it's in Z, we say that the congruence of A mod M is all the B's in Z, so that we have this relation. Like that might sound a little bit familiar. Let me take you back. If we have that this is a relation, then this right here is the definition of an equivalence class. That was the A/R. So we could define AM or A mod M being the same as the equivalence class. So that's another way to think about it. And then last way, probably the easiest way that we can think about it is using the theorem that we just proved, and that's just you take A and you keep adding M's to it. And when you're making a calculation, that is definitely the fastest way. So let's go ahead and use that theorem to find the congruence class of 2 mod M. Certainly, if K was 0, we would have 2. And then we can add 7. Then we can add 7 again. And then we can subtract 7. And we can subtract 7 again, which is going to be a negative 12. There we go. And then we have 9. And we can say that 9 is definitely in its own congruence class. But we can also add 7. And we can add 7 again. And then we can subtract 7. and subtract 7 again. You should be able to see that these sets, if you keep writing out more elements, they're going to be the exact same thing. That is not a coincidence. That stems from the fact that 2 is equal to 9 mod 7. We know this because that's the definition of 2 being in the congruence class of 9, is it has to fulfill that, right? There it is. So with this knowledge, let's move on to a theorem. Ah, that looks familiar. If they are congruent mod M, their congruence classes are completely the same. So let's go ahead and prove that. We're going to go forward first. We're going to say, if we go forward like this, that means we're going to assume A is congruent to B mod M. And then we're going to work towards these sets are equal to each other. I said the word sets, that means we're going to start doing some element chasing. So we're going to say assume this fact, and we're going to let C be an element of the congruence class A mod M. There we go. By definition, we know that C is then going to have the form A mod M, or it's going to be congruent to that. And now here's the part where I said you want to remind yourself that R is a equivalence relation. We know that R is transitive, which means we could move this over to B mod M. So we have A is congruent to B mod M, C is congruent to A mod M. Therefore, by transitivity of R, so R is transitive, we get that C is going to be congruent to B mod M. Then where are we trying to get? We're trying to get it into this set. And we are there, by definition. Now we ask ourselves, in order to get that they're equal, we have to chase it backwards. We have to start here, end up here. Can we reverse these steps? Yes, that one reverses. Definition of being in the congruence class. That one reverses, still because of transitivity. That one reverses because, definition of being in the congruence class of A. So let me get rid of the extra words. And we're done. So that's the forward direction. We have now proved congruence class of A equals congruence class of B. So now we would like to go in the opposite direction. We're going to assume that the two congruence classes are equal. Let's write the word assume. Assume congruence class of A mod M is equal to B mod M. And we are going to work to a point that says A is congruent to B mod M. So what we know, I know that A will be an element in here. Why do I know that? A is equal or congruent to A mod M because, remember R, it is, let's see, so equivalence relation is, we did transitive, it's symmetric, and it's the last one. Oh man, why do I always forget this one? It's reflexive. Remember, reflexive means that A comma A is going to be an R for all of the A's. So that means A equals A mod M. So then from there, we can say that A is an element of the congruence class of A. That means that A is an element of the congruence class of B. which means by definition of congruence class, oops, A has got to be equivalent to B mod M. There we go. And that's both directions. So we are now done. Now we're going to use this to get a couple of cool lemmas. First lemma is that we have, I'm going to point out real fast that like when 7 divides 9, it doesn't divide it perfectly. So we could use the division algorithm to write 9 equals 7 times q plus r, where r would be the remainder. In this case, r would be equal to 2 because q would equal 1. And 9 is going to be equal to the equivalence class, that is its remainder, 2. We already showed that on the previous page. We already listed out some elements, and we said, yes, these congruence classes are equal. In general, that holds. If you take m dividing some a, and you get a remainder of r, the congruence class of A will equal R. That will fall out pretty quickly, and so I will leave that proof for you guys to do on the worksheet. Moving on to something that falls out maybe a little bit less quickly is any two congruence classes modulo M are going to be either disjoint or completely identical. So there's no in between. No, we're going to share one element and the rest of our elements won't be shared. So this proof divides into two cases. We're going to assume that A and B are integers. Oops. A and B are integers. And then, let's see. So either, remember, they're completely the same or they have nothing in common at all. So to me, that says we have cases. We have case 1, their congruence classes have no overlap, aka no elements are the same, they are disjoint. So if we are in this class, or this case, we're done. The next case we have is maybe they do have some overlap, and our job is to prove that if they have even the slightest bit of overlap, even one element, they are completely the same. So that is the same thing as saying our second case is going to be it's not the empty set. So there is at least one element that is in both of them. So then there exists some element C that is in their intersection. Then we can write that out using the definition of intersection. So then by definition of being in those congruence classes, you end up with C is going to be congruent to A mod M, and C is congruent to B mod M. So then that means congruence class of C is equal to the congruence class of A. That was the theorem that we just proved, I think the first theorem that we proved. There we go. Right, it's that one. Yeah. Okay, so the theorem that we just proved, C is equal to A mod M, therefore their congruence classes are equal. So now this guy equals this guy, but this guy also equals that guy. So now we take those pieces of information, plug them together, we get A. Its congruence class is going to equal B's congruence class. Oh, that is a tongue twister. I can't say that. And that's it. We are done. Okay. Next thing that we're going to do is, since we have, they're either disjoint or identical. The question is now to me, like, exactly how many can we have then? The answer is we can have exactly m for anything that's been modded by m. We have exactly m distinct congruence classes. Specifically, these are going to be them. Note, we do not have the congruence class m mod m because m minus m, like that, that's 0. So this guy, not that one, is going to fall into, why can I not draw an arc right now? It's going to fall into that congruence class, into the congruence class of 0. So it stops at m minus 1. So this is going to, the way this general proof is going to go is we're going to show that we have no more than m, and then we're also going to show we have no less than m. So if we can't have less and we can't have more, it has to be exactly m. So proof. I'm going to use the lemma that you guys are going to prove on your worksheet first. We know that the congruence class of A mod m is equal to the congruence class of its remainder mod m, where when you do m divides A, it has a remainder r. Okay, so that specific r. And we know that the remainder is always going to be greater than or equal to 0 and less than m by a lemma from earlier. So then we have, so we can't have more than m many, right? Because we only have m many choices for r. Okay. So that means we can't have more. Now we're going to show that we can't have less. The way we're going to do that is we're going to show, so want to show for the next part that 0, 1, keep putting my commas in the wrong spot, all the way up to m minus 1. We want to show that these guys are all different. There we go. And we can do that by showing that like 1 isn't in m minus, an element of m minus 1. Because 1 isn't m minus 1 mod m. So remember, if 1 isn't in m minus 1 mod m, that means that this guy and this guy have an element that isn't in common. So these guys, we have 1 here, but we don't have 1 here, which means they have to be completely separate. They don't overlap at all. That was the theorem, or the lemma, the second lemma that we just proved. So I'm going to take 2 random elements, let's see, without loss of generality, let 0 be less than A, be less than B, be less than M. Okay, so I have 2 elements between 0 and M, or including 0, but not M. The without loss of generality is because I said A was going to be less than B, because we know we don't want to look at A equals B. That's a boring case. That's itself. Of course, they're going to be the same. We're looking for 2 different elements between 0 and M, and we want to prove that their congruence classes aren't going to be equal. So here's a random element, here's a random element. We're going to look at their congruence classes, and we are going to conclude that they are not the same. Okay, that's what we're working towards. How we're going to do that? We're going to say, we're going to, let's see. we could get that if like B isn't an element. So really that's our real goal, is this. We want to prove that B isn't going to be an element of the congruence class of A, which means we want B to not be equal to A mod M. Okay, this is one of those cases where like you see what you need from the bottom, but not so much from the top, I feel like. So we want these guys to be empty. We don't want them to overlap, which means B won't be in here, which means it won't be A mod M. So that means M won't divide B minus A. Okay, now we're working somewhere very close. What can we say about B minus A? Well, I know B is bigger than A, right? B is bigger than A, so it's going to be bigger than 0. Actually strictly greater than 0. And we know that B was less than M. Since A is non-negative, we can't get anything bigger than M, so it's less than M as well. So we have a number that is less than M, means it won't be able to be divided by M. So that means this jump right here, so this one came from what we just did. This comes from our first line. Comes from here. But then this line will imply this line. So we have basically closed off our proof here in the middle because B minus A is less than, or because M doesn't divide positive numbers smaller than itself. Right? You can't have 7 divides 3. That's nonsense. So then moving on from there, that means it can't be congruent to A, which means it can't be in the equivalence class of A, which means that their intersections have to be empty. And we are done. Okay. So now that means none of the equivalence classes overlap. The equivalence classes overlap. And if none of the equivalence classes overlap, we can't have less than M many of them. There we go. Therefore, there is exactly M many. All right. So kind of in the vein of which congruence classes we can have, we're going to define a new set. So we're going to define something called Z mod M. It is just the set of integers starting at 0 and going up to m minus 1, just like the congruence classes. You can only have like 0 to m minus 1. Those are the only possible options. So then Z mod 2 would just be the elements 0 and 1, which you'll notice is the same set as possible remainders if we were to be dividing by 2. Not a coincidence. Then this guy is going to be 0, 1, and 2. This guy is going to be 0, 1, and go up to 5. So the congruence classes of Z2 then is just going to be congruence class of 1 and 0, because those are its only elements. So if we look at 0, remember Like the fast way to calculate it is to take 0 and then add 2 and add 2. Subtract 2, subtract 2, like that. And then for 1, we do the same trick. We start with 1, we add 2, we add 2, we subtract 2, we subtract 2. And I think you guys can probably see at this point the congruence class of 0 represents all evens, and the congruence class of 1 represents all odds. Okay, so that's kind of a fun fact. Now we're going to start defining what it means to like add and multiply within a congruence class. Like we know 2 and 4 are elements in Z6, but how do we add them together and stay in Z6? Like 2 plus 4 is 6, and that is not an element in Z6. It stopped at 5. So the way we're going to define addition and multiplication is a plus b with this little subscript of an m is going to just be a plus b mod m. And then a times b with a little subscript m is a times b mod m. So if we were to look at this, this would be the same thing as 2 plus 4 mod 6, which is going to be 6 mod 6. And then, yeah, sure, that's equal to 6, but we want to stay here in Z6. So out of these options, what is that going to be equal to? Well, 6 divides 6 minus 0. So that's going to be 0. Okay. Then same thing here. We're going to say that 2 times 4 mod 6, which is going to be 8 mod 6, which if you do 6 divides 8, we get a remainder of 2. So 2 would be its result in Z6. And then these operations operate a lot like before. Like it doesn't matter what order you add in, it doesn't matter what order you multiply in. You can do it backwards or forwards. 0 works the same. You can add it to A and you'll still get an A. 1 works the same. When you multiply it by A, you get back A. Even distribution works the same. And then this one, I thought this one was kind of weird. Like this is kind of the hardest one out of everybody to wrap your head around. You've got X coming from ZM, and it's going to be A plus X mod M is going to equal 0. So that is technically called the additive inverse because we like fancy names. And I'm going to cover how to find that in just a sec. But let's just work on computations. And I apologize. These M's right here should have been 6s. There we go. I think that's all of them. So that would be the same thing as doing 4 times 3 plus 5 mod 6, which 3 plus 5 is 8 times 4 is 32 mod 6. 6 divides 3 and has a remainder of 2. So there you go. We have stayed in Z6. And then here, for this next one, we've got X is in Z6, and we want to solve this equation. So now we're not going to solve, this equation. Because then you can kind of look at that and you're like, X is -2. Like, nope, not here. -2 isn't in Z6. So how can we do this? So what we need to make use of is 0 is equal to 6 mod 6. And so we're going to think of this problem. I'm going to try and find the X that adds to 6 because that will get mapped back to 0. So then X is equal to 4. So then 2 plus 4 mod 6 will equal 0. And that's how you find how to add to 0 in these special sets, Z mod M. And then our last example is going to be 2 times 3 in Z6. So that's 2 times 3 mod 6, 6 mod 6, which is 0 mod 6. So there you have it. This is what it takes. This is like the kind of sets and the set operations that we need to be using in order to start with a non-zero number and a non-zero number and somehow end up multiplying to 0, which I think is just like radically cool. But anyway, that's all I've got for you guys right now. And so I will see you later.